everyone, and welcome to today's live stream event. My name is DJ Frye. I'm the Director of Food Retail for the North American market. Alongside me is Dean Groff, our CO2 Hotspot Champion. Before we begin today's event, I would like everyone to know that this is being recorded and will be on demand. Also, after our tour, we will be hosting a Q&A event. Dean, through all my travels and roles leading up to today, I've never witnessed anything like our Danfoss Smart Store. This is a turnkey, natural refrigerant, functional, live store, grocery store. This is amazing.
Yep.
As we in North America continue to navigate through refrigerant and regulation changes, it is reassuring to know that our partners globally with Danfoss have the know-how and experience to help us on this journey. Dean, with all that said, with your tenure and experience with CO2, would you like to share some things before we start this?
Yeah, I sure would, DJ. You know, in 2020, the World Economic Forum came out with a list of drivers that could lead us to net zero buildings, right? And they called these the good deeds, DEED, right? And the first one was decarbonization. We're going to use more electricity in the future. So we need to start sourcing that from more renewable resources where we can, where it makes sense, right? And then the electrification of the buildings as they move away from fossil fuels for heating the building and for heating hot water. That's going to create even more demand for electricity than what we see today. And so as that demand increases, the second E is efficiency, right? The electricity that we use, we need to do it in the most efficient manner possible. And then the last one is digitalization, where we can allow all of this equipment that we use in all these buildings to talk to each other, to work in harmony together, to use the electricity that we have in the most efficient manner, right? And that's what we're doing with our ADC and our Smart Store, right? It's centered around taking these good deeds and using them to the best of our ability as possible. Everything from cooling to heating, from the sensors to the cloud. And this technology that we're going to see is scalable. It works in a convenience store all the way up to a large warehouse if you wanted to. And this Smart Store that we have includes everything that's efficient, like from solar panels, geothermal, heat recovery. It's got biodiversity. It's got gray water collection in it. The refrigeration system itself runs off of CO2, so it's a natural refrigerant, right? And it uses the Danfoss Calm adaptive technology, which gives you even more efficiency on top of that. What I think is really cool about this, DJ, is that this isn't a science project. It's off-the-shelf technology. If you were a retailer today, you could use it and implement it if you wanted to, right? The store itself, it's about 8,000 square feet, roughly 156,000 BTUs of cooling. It's got other things in there too, because it is an operating food retail store. It's got a car wash. It's got a fuel station. It's got charging stations for electric cars. It's got everything you would see in a supermarket, right? CO2 racks. It's got display cases. It's got some independent coolers. It's got a few cold rooms, but it also has some things you wouldn't see in a normal grocery store. We're going to see that. So, man, I am really excited about this. And if you're ready, let's turn it over to Ejnar and Drew for the tour over in Denmark.
I am super excited. Let's go, guys.
Okay. Sorry. No, I'm good.
All right. This is the back entrance to the ADC. We're now going to walk in here and have a conversation with Ejnar, who runs and operates the system. Now we're inside the ADC with Ejnar. Ejnar, can you introduce us to the building and the system?
Yes, I can. And welcome to the Danfoss Smart Store ADC. ADC is our application development center. We have different application development centers around the world. But this one is a little bit special because what we are testing here is a running system. We have a live supermarket just next to us, and the most important is to keep the goods cold. And so we can also say that all the technology that we have here in this building is technology available for our customers today. And there's nothing like half-baked cookies or anything like this. All the products are available. We have a lot more products in here and systems than you would normally see in a small supermarket in a cold climate. This is the discount store. It's 800 square meter of a sales area. And normally the machinery room would be 12 square meter, or the size of this entrance. We have 240 square meter, and some people think, what a waste of space. But again, we are showcasing technology not just for small supermarkets in a cold climate like this. We also have technology which can be used in large supermarkets, hypermarkets, in hot climate, like in the US, where we see a lot of those supermarkets. But I think what is important is for us to take a look at how we're optimizing the energy stream. So let's move over here and take a look at that.
Working with sector coupling solutions, I'm of course most interested in the energy flows. Can you explain to us what we're showing here in terms of the smart store?
Yeah. What we do see here is all the different applications in our small supermarket. And starting on the top, we have 100 kilowatt of solar panels installed on the roof. We have two CO2 pack systems installed, or rack systems that you call them. One which is a standard system, which is specified by Coop for such a small store like this one. And then we have a second pack, a little bit more advanced one, where we have all the technology that's actually can be used more or less all over the world. We have the evaporators at the cold rooms in the store, like in a standard store. So we are doing the operation of a standard supermarket. We connect it to the electrical grid, so we can buy electricity, but of course we can also sell electricity if we have too much. We have an external district heating grid, so we are actually getting all the heat needed for the building. We can buy that from the district heating, but we can also send back or sell back energy to the district heating if we have excess heat, which we do have in summertime. We have a ground loop out here in just next to us, so we can take out about 20 kilowatt of the heating capacity from the ground. So what we do, we connect that ground loop in the same way as the cabinets are connected. We connect that to the refrigeration system because in winter time there's not enough energy or heating in the goods for us to heat up the building. So then we have extra heat from the ground we can take out, connect to the refrigeration system, and in this way we can actually produce a lot of heat even in the winter time. We can do de-icing in front of the building. We have lots of components from our heating division for optimizing hydronic flow, which is also extremely important to optimize such a system as we have here. We have car charging, which we need to have by law. We also have prepared for a fast charger. So if I had a Tesla, one of the bigger ones, this one car would take 3 times more energy than the whole building here running peak, 3 times more. And that means going forward, we will be asked to deactivate energy capacity very fast, because when all of us are driving an electrical car, our grid system cannot do it. There's not enough capacity for all of us to charge at the same time. And therefore, the whole industry will be asked to be able to deactivate energy. Also, with all renewable energies we see here, the windmills and the solar panels, that's also a stress factor for the whole energy system. We have not yet installed a battery. It's on our plan. It will be done this year. We have some cold water for air conditioning, comfort cooling, and some also a little bit buffer for hot water and lighting control, HVAC control. So all these are the energy streams we are actually going to optimize. But why don't we go inside and take a look at all the technology and see how it works in practical?
So Ejnar, now we're standing in front of the standard pack control or pack system for the supermarket. Can you tell us more about this system?
Yeah, this is a pack or rack, as you call it in the US, which is specified by Coop for a supermarket like this size in a cold climate. Very standard system. Of course, the CO2 natural refrigerant using Danfoss drives, Danfoss box compressors. And it's also built with the heat reclaim on the system here. And when we are seeing how we are taking out the heat from a refrigeration system, we do it by means of the heat recovery unit. So Anja, if you can, let's see over here. Here we have a Danfoss heat recovery unit. And this heat recovery unit is something we have built because our customers, when we're talking about refrigeration people and heating people, they don't understand each other. It's like 2 different species. They are talking like this. So what Danfoss did, we have built this heat recovery unit, and by means of a simple 0 to 10 volt signal, we can actually have the pack controller, the Danfoss pack controller, communicating with this controller and the heat recovery unit, and we take out all the heat that is possible without sacrificing food quality. I think we will take a look at the picture, how it works in real. So let's take a look at that picture.
So now we're looking at the operating screen for this standard CO2 pack. Can you explain more about it?
Yes. We have the medium temp compressors, low temp compressors. Here we have a heat exchanger, and we can take out heat to the heat recovery unit from the system. As also mentioned earlier, we have a ground loop or a false load, so we can connect the extra load to the system when we need that in winter time. And the heat recovery unit is something Danfoss has built because what we have learned here in Europe, at least in Denmark, is that heating people and refrigeration people, they are two different species. They don't understand each other. It's like talking like this. So what Danfoss did, we have built such a heat recovery unit, and by means of a simple 0 to 10 volt signal between the pack controller and the case control, we are actually getting this up and running. And let's take a look at the heat recovery unit itself. Here is where we are buying heat from district heating into the system. Here is where we are sending out the heat to the building. This is where we're getting heat from the refrigeration system. And we can see it's coming in with 73 degrees centigrade at the moment. And here we are selling back to heat to the district heating. Unfortunately, district heating only want a heat above 63 degrees. And we can utilize a lot of the heat below 63 degrees. By having our own system connected, we can actually utilize all the heat generated from our refrigeration system. We did a test last winter, just before Christmas here, where the ambient temperature was -6 and in nighttime, and between -1 and 0 in daytime. And we produced 150% of energy. 100%, which was needed for the whole building, the store, and the Danfoss area, and then 50% on top, which we could sell back to district heating. And that temperature was above 63 degrees. So yes, we can produce all the heat needed for this building just by means of our standard refrigeration system.
That is impressive. And we'll look at that energy balance and the meters on it here in a minute.
Yes.
So Ejnar, we just looked at the standard pack which is a backup for the main system here. And now we're looking at the main system, which is also a system that has been designed to handle more of your hotter climates, such as the southern US market. Can you speak to this?
Yeah, as said earlier, the standard system is for a small supermarket here in a cold climate. This is a system which is suited for, I would say, more or less a hypermarket in hot climate. We have the Danfoss drives, we have the Danfoss box compressors, we have ejector technology, and the ejector technology is definitely something which is important when we are going to a hot climate with a high temperature, and because there we can really gain a high efficiency of a CO2 system even in hot climate. So it's not something which only can be used in a cold climate like this. And another thing is that we also are using this pack not just for cooling of the goods and for heating of the building, but we're also doing comfort cooling by means of this system. So all three things can be done with the one pack. So we call it more or less an energy pack. So, but again, as you can see, a lot of components. An important part again, the ejector, and the ejector can be used for two different things. First of all, to make a system running effectively in a hot climate, but we also have a liquid ejector function in there, so we can run our system not flooded, that we're saying, but nearly flooded, and that means that we can increase the suction pressure a few degrees, which give us between 5 and 10% of savings by having this extra feature with the ejector. So you're actually getting two things out of it. So again, very effective. And when we are looking at the energy which we are harvesting here in summertime, because in summertime a refrigeration system is already running as a heat pump because of the high ambient temperature. And because we are connected to the district heating system, we can sell that excess heat. And I will show you on the meters over here how much energy we have bought for the building and how much we have generated by the packs.
So Ejnar, in sector coupling solutions, we're most interested in the energy balance for the facility, i.e. how much are we producing versus how much are we purchasing? Can you tell us about that in terms of heat for this facility?
Yeah. First, just this is the interface to the district heating. So it's not owned by Danfoss. It's actually owned by the district heating company, and it's their meters. But when looking at it, this is what we have bought of energy from district heating since we started last year in May. And this is what we have sold. And as you can see, how much have we been buying?
82, 87 kilowatt hours.
And sold?
26.3 megawatt hours, so 26.4.
So this is what we have sold since we started the system.
Yeah.
As also mentioned earlier, we can also run the system so we can produce heat. For instance, if we have excess energy from the solar panels, which we are normally selling then back to the district grid or to the grid system, electrical grid system, instead of selling that back for nothing, we sell it back as heat to the district heating. And we have, out of these 26 megawatt hours, 9 megawatt hours was produced by increasing the pressure. The rest of it has just been something we have captured as excess heat. And what would happen in any supermarket would that all that heat which we have now sold back would go out to the birds through the gas cooler. And there's so much heat to save, or so much energy to save, if we can capture that energy instead of sending it out to the ambient. And every supermarket, in every refrigeration system can do this. I think this is at least something we should take a learning from.
So roughly 15 megawatt hours was normal operation excess heat, if you will.
Yes.
And then we had an additional 9 megawatt hours, which was produced and utilized for our own facilities in the campus energy system or district energy system because we could.
Actually, on top of that, what we were using for the system here was produced on top of these 26 megawatt.
Oh.
So 22 megawatt was used for the building itself, and 26 was sent back.
Wow.
So
impressive.
Yeah, it is impressive.
So Ejnar, we're still standing in the technical room, but we're also standing right in front of the glass doors for the grocery store or the supermarket that this is serving. When we do an application development center, what is really critical is that we're trying to demonstrate and show how to do the system design utilizing our full portfolio of components. Can you explain some of the examples of the components that we're utilizing as a part of the system?
Yeah. Actually, as many people know, Danfoss is more or less a component supplier, and we have a lot of knowledge in the different components. And what we did here was that we built a complete supermarket also to get a full understanding about how to build this together in one system, and also how to learn how can we optimize this system. We have the system manager, or kind of the building management system of the system. So all the controllers are connected to the system manager, and this one again connected to the cloud, so we from remote can monitor the system. We have the CO2 pack controllers, which is also controlling the ejector we stored earlier on the pack over here. It's a controller which is a decentralized controller to take care of all this control of a CO2 pack.
So that is the critical factor in controlling, for example, for the hot ambient climates, how you enable a CO2 system is the combination of this with this.
Yes. And what you see in the US, you normally use a lot of the IOs. We also have, so we can connect the IOs to this. So depending on the size of your system, you can actually have a more or less IOs connected to it. And then we have the case controller, the CC55 case controller, which we have here. And this one is sitting in each of the cabinets using our electronic injection valve and sensor and displays and so forth. And all this are connected then to the system manager. And on top of that, we have the heat recovery unit connected. We also have some of the heating ventilation system connected in our complete system. And again, this is then connected to our Alsense platform, so we can monitor. For me, it's more or less easy to monitor one store, but if you have a total fleet of stores, you really need something like the Alsense software to overview and monitor the whole thing. But I think we will get a little bit into the details about the learnings we had, how to optimize, not optimizing, sub-optimizing one component, but trying to find the compromise for the whole system. But we'll get to that.
Interesting. Yeah. Let's go look at that. So Ejnar, we've looked at a lot of screens here, and this is the one that is, as I understand it, pulling together all of the information from everything else we've already looked at. Can you run through some of that?
Yeah, actually, the the system manager is the controller, which is connecting to all the different controllers. And what we are showcasing up here is the cold rooms, the medium temp, low temp, cabinets, and medium temp cabinets. So, of course, for a grocery store, the most important is to keep the temperatures at the right level. So this is mandatory that all this is monitored, and this is done by a monitoring company 24/7, as we see all over the world. And then also it's connected to our Alsense software, so we are benchmarked with these stores against other stores. So they are really watching me if I'm doing a good job or not on our system. But again, having all this connected through to the cloud system is really what is important when we are talking a chain monitoring. But again, the system manager doing the integration to all the cloud information.
So, Ejnar, from what I understand, that advanced pack that we looked at earlier is also providing the cooling for this building. Can you explain what we're looking at now and how that ties back to that?
Yeah. When you're using the advanced pack, we can do the air conditioning or the cooling by means of chilled water. So we are cooling or chilling the water by means of the advanced pack when we are using that one. When we are using the standard system, we have an extra chiller on the roof as a kind of a backup system for that. So cooling down the water, and then we're circulating that cold water up to the air handling unit, and by means of this we are doing the cooling. In the beginning, we also had an idea that we could connect an ice bank to it, and but we're looking at the price level for an ice bank and the size of it. We cannot see that it makes sense for a supermarket itself, but there could be new kinds of ways of buffering up. So we have prepared it a little bit on the side here, so we can add a buffer to it when that comes at a reasonable price level.
And it is an ADC, so we want to potentially do that research, right?
Absolutely.
See if it makes sense.
Absolutely. Yeah.
So, Ejnar, we're now looking at the air handling unit that supplies the comfort heating and cooling for this building. Can you tell us of the learnings as a part of the optimization of this system?
Yeah, it's a pretty standard air handling unit for a store like this. We do have a heat recovery wheel inside here, and when we had the commissioning engineer doing the optimization of this system last year, he came very proud to me and said, now I got the performance of this wheel up above 80%, which is what you can do. And I said, so what? And he was a little bit frustrated, I believe. But anyhow, a few months later, I started looking into how to optimize the system. And the first thing I did was that I reduced the speed of the fans. If you open the one there, you can see we have the Danfoss strides in here. So reducing the airflow or the speed of the fans by 10%, we saved 20% of energy on the fans alone. Yeah. And the energy consumption for the fans is a pretty substantial part. We do have the meter, the energy meter for the fans. I have a meter for hot water, for cold water, so I know exactly how the energy flows is for this small unit alone. But again, reducing the airflow, then there will also need for less heat for heating up the building. And the performance dropped to 76%. Huh. And know what? We were saving energy on the complete system. In the
total energy balance,
yes.
We were saving energy.
And this is exactly how we have to look at it, not trying to sub-optimize one part of the system and trying to optimize, find the best compromise across the whole store. And in this way, we have been looking at the ventilation system, the hydronic system of the flow, how to optimize that, the heating system and the refrigeration system to have that running in the best way with the best compromise. And I'm sure that's where you can start saving energy across the world.
So one of the fascinating subjects for us in the sector coupling team is the transition of energy consumers to being energy consumers and prosumers. So potentially at points in time selling energy and buying energy, depending on the energy balance of their own facilities. And what we see as a fascinating subject within that is the opportunity to, in the future, utilize solar panels, which we see here on the Smart Store, to utilize or to produce electricity that we either utilize in the facility or that we sell to the grid, or utilize that electricity to produce other forms of energy. And I spoke to earlier another application development center that we're planning to do based on our own solar field across the street over here to potentially produce hydrogen for our own facility usage, for our own production usage, which that's another form of energy storage, such as the cooling tank that we saw downstairs earlier. But the opportunity also to utilize that energy to produce hydrogen and at the same time use the inefficiency of that electrolysis process to recover heat to supply to the district energy or campus energy system and then to the district energy system. And another form of that is also just producing heat in general. So utilizing the electrical power, if the heat price is high, to at that same time utilize that energy and the electricity price is low to produce heat to sell that to the campus energy system and or to the district energy system. Ejnar, can you tell us about what we're doing here at the Smart Store in terms of baseline research on how you create that energy arbitrage system of the future?
Yeah, as you also saw in the beginning, we have all the different applications, and what we have been testing is these different handles. How much capacity can we push or move around in a standard supermarket? With the solar panels, the 100 kilowatt of solar panels installed for the first half year of 2024, 37% of the energy use, electricity for the store alone, was supplied by the solar panels. And on top of that, we were selling for the first half year only 12 megawatt of energy back to the electrical grid. A little bit of that we used for testing. We're running our refrigeration system as a heat pump. So taking that excess energy from the panels into the refrigeration system, produce heat for the district heating and selling it. And the positive things is that we are getting more money for the energy we are selling to the district heating grid as what we are getting when we are selling back to the electrical grid.
Makes sense.
But that will probably stop one day. But we have been testing on all these different handles. We have also tested how we can buffer up energy in the cold rooms and the low temp cabinets if there's something we can store there. It's not a lot, but if you take a total supermarket chain, it's all add up. Yeah. So we have now an idea how much energy we can store and buffer up across and with what kind of timing. But we still need the full sophistication to get all the pricing and data and build all that. So that's the next, I would say, the next step for us.
So Ejnar, we saw downstairs that the advanced pack and the standard pack are both the primary cooling system for both the refrigeration and then also the cooling of the facility, the comfort cooling of the facility itself. Can you explain what this is doing in addition to that?
Yeah, when we are running with the standard pack, or if there's extra heat need for cooling, then we can run this CO2. It's actually an Optima condensing unit, which we are using, or we could say misusing a little bit, because we are building a heat exchanger on the side here, and we are using to chill the water for comfort cooling. But again, also a CO2 unit. So all the refrigerant we are using here is natural refrigerant CO2 in the whole store here.
So Ejnar, now we're looking at the gas cooler system, right? And yes, this is what is, along with the ejector system that we saw downstairs, what is really critical to enabling the operation, efficient operation of a CO2 system in a hot ambient climate. Can you speak to what we're doing here with the gas cooler and how it helps enable that?
Yeah. First of all, we doesn't need it here in Denmark because we have a cold climate. But we have installed it to showcase for our customers coming from all over the world what can be done, but also for us to learn how to control and improve the control. But with this adiabatic gas cooler, we can actually spray water on the side here, and we will only spray that amount of water needed that is evaporating. So there's not a lot of loss of water. That's one good thing. And the other is that by having this cooling efficiency, it's like when you're sweating, you know, getting water on the surface up here, then you're also having a cooling efficiency by that. And that's exactly what is happening here. And it will give us about between 5 and 7 Kelvin of extra cooling, which is extremely important when we go into hot climate, because it's a very efficient way of getting the system running in an improved way.
And those hotter climates tend to be the drier climates. And so you have more of that dry bulb versus wet bulb separation. which this creates that opportunity for. So Ejnar, we talked about the criticality of showing examples of and demonstrating the use of our components as a part of these systems. And the history of the development and evolution of those components becomes really critical to the story that we tell in these application development centers. Can you speak to that?
We only see a small part of the product from Danfoss and very much related to supermarkets here, but Danfoss actually started with this first mechanical expansion valves. The first version of a case controller more than 30 years ago. It was introduced in 1987. We are at the 6th generation today. Full store control, as we saw in the US, starting with not just the HVAC and but also the refrigeration system integrated. We started very early here in Denmark because of taxation of HFCs. We were forced to do something, and already in around the year 2000, we started, and I think in 2002 we had the first supermarket up and running. So for more than 20 years, we have now been working CO2, and I would say most of Europe, they are using CO2 as refrigerant today.
So it's become standard in Europe.
It does. It does. And it definitely
even in the hotter climates.
Yes.
Within Europe.
Yes. As you say, Spain or Italy or going down there. We also heard about the possibility of now harvesting the energy from such a refrigeration system, not just looking at one part, but looking at the whole system. And it's so important that all this can be managed and integrated in one system. We have 50 meters across electrical meters, meters for hot water, meters for cold water, and 3 meters for tap water. And you cannot manage what you can't measure. And that's also, I showed you up at the air handling unit. We have meters on all kind of the details, so we have a very nice idea about what's going on. One thing we have been testing, something which has been there for years, is rail heat control. And we had issues with the moisture last year, just after the system was built here, because there were a lot of moisture in the concrete as well. But again, I called the contractor, and he came and he put rail heat at 100%, and then flat out it was running. When the humidity level decreased, I started setting up our controller with the built-in functionality. So we are running rail heat based on dew point. And what we can see, we are saving a lot of energy on rail heat alone. Just in this small store on the low temp cabinets in those 4 groups, it's a 2.6 kilowatt. And this is adding up to 22,776 kilowatt hours per year just for rail heat when it's running 100%. And in wintertime, we can run it as low as 30% and saving a lot of energy. And the biggest learning here is that when we are running 100% rail heat compared to 30% rail heat, the pack will need 15% extra energy. There's an extra 15% of energy consumption on the pack just to remove the energy you put into the cabinets by means of the rail heat. So because we have that knowledge, we are now trying to tell to the supermarkets how important it is just to control a small bit like this. People think it's peanuts, but it's not. Here we have one store, and it's easy to monitor one store, but if you have a fleet of stores, you need, again, something like Alsense connected to a cloud system and helping you to do all that monitoring. And I think this is at least what we can see, the adventure going on here.
Yeah. So Ejnar, thank you once again for the tour today. What we learned from this tour is that to optimize the energy flows, you first have to measure everything, and that CO2 is not new. That it has become the standard in supermarkets across Europe, including Southern Europe and those hotter climates.
Thank you, and thank you to all of you as well.
And with that, we'll go back to you, Dean.
Ejnar, Drew, thank you all so much for your time and taking us on that tour. Everyone, during this tour, we've received a lot of questions. So during this remaining time, Dean and I are going to try to divide up these questions and tackle them. We have resident experts online as well to help answer these. So with that said, I'm going to jump into the first questions here. Ejnar, I believe this one's directed, maybe you can help us with this. What is the chilled water temp supply to the AC units? How is this controlled with Danfoss controllers? And adversely, can the heated water also be used to heat a space?
The water temperature we have in the tanker, the target is 8 degrees centigrade, which is 46 Fahrenheit. So that's what we are aiming for, and that water is then used in the air handling units. If we can use the same circuit for both heating and cooling, at least we have 2 different coils, one heating coil and one cooling coil in the air handling units. So it's 2 different systems, 2 separate systems. But both the air conditioning, the cold water and the hot water is coming from the advanced pack, but from 2 different circuits.
Wonderful. Thank you, Ejnar.
And how is it controlled? We are using one of our programmable controller, the MCX control, where we did the software to control the tanker temperature and also request the refrigeration or the cooling, the air conditioning from the advanced pack.
Outstanding. Thank you very much. Dean, another question coming through?
Yeah, and again, I think, Ejnar, this question is probably for you. It says during the tour, you had mentioned some adjustments that a contractor made to combat moisture issues on the cases, and then that led to an increased energy usage. How did the Danfoss controls work to help alleviate this issue?
You're talking about the anti-sweat control?
Yes, I believe so. Yeah.
Yes. When we had a lot of the moisture last summer, and as I also said, there were a lot of moisture still in the concrete because it was a new build, and there were really nothing the rail heat could do, even if it was running 100%. But the refrigeration technician, he came here on the side and he put the minimum rail heat at 100%, and then he left. He said there was nothing more he could do. And there's a lot of these things going on, and will that ever be put back to a control again? Very often it will not. And when the humidity level was then reduced back, or it was a lot lower than in the months of November, I started setting up the anti-sweat control based on dew point control. And the whole winter, we were running as low as 30% on the anti-sweat instead of 100%. And I think the learnings is that if there's an issue with condensate, a refrigeration technician could put this anti-sweat at 100% and leave it there, because at least then he cannot do anything more. But what has to be done is you have to look at the air conditioning system to ensure that humidity is controlled by your air handling unit, or whatever you are using for dehumidifying. So this is where we have spent a lot of our resources also here during the summer to get the air conditioning system optimized to ensure that we have the right humidity level in the store, not to get condensate in. But there's so much energy which can be harvested. I know this has been going on for many, many years, for centuries. And it's amazing that people still just put it 100% in many stores and forget that it's really an energy consumer.
Excellent. Thanks, Ejnar.
Great. Along the lines of energy, Mark, Ejnar, either one, are there any design changes that can reliably save energy, generate income, that are passive or simple to the point that changing one setting doesn't create a large energy cost?
Mark, do you want to take that one, or should I? I can start.
Please, you.
There's definitely one setting which can you can change, and then you will see that your refrigeration system is not running optimum anymore. Just the suction pressure, if that is lowered, and that's also happening very often when there's a high temperature alarm in a store and a refrigeration technician comes to the store. It could be that he just reduce the suction pressure to ensure that he get a bigger delta T, and perhaps it doesn't really help on the system. It could be a broken fan or an iced up coil which was giving the issue. So there's one parameter which could really make the system running extremely ineffective. But again, there's a big number of parameters which has to be, I would say, optimized between each other and finding the right compromise. And perhaps you have something here to add, Mark, on how you see this?
Well, I'm more focusing on the design of the system, and very often what we see on other systems is that sizing of components are not correctly done. And for example, it was not pay attention to have a linear capacity control on the compressor side, and then you have a kind of steps in the capacity, which creates challenges to fine-tune the system. And this is especially important when we are using, for example, parallel compressors to control pressure in the receiver, as the volume between the gas volume between the receiver, CO2 receiver, and the suction lines to the parallel compressors are quite short. These compressors are really sensitive to the variations of the load on the receiver, and all this, if it's not fit correctly, creates instabilities not only to the receiver pressure control but to the whole system. Maybe we can share some learnings from our side regarding the gas cooler. It's a V-shaped gas cooler, and it creates for us a quite big challenge to fine-tune the operation of the fans on it. Because of this geometry, it's a little bit tricky to find the right values. And of course, if you have instabilities on the high pressure side, it creates instabilities in the rest of the system. So it was quite good learning.
We can also say that a adiabatic gas cooler is actually not something we need in our area. We could easily have been running without it. So it's optimized for hot climate. And that's also probably one of the reasons why we are having a little bit more to do the optimization of that one.
Yeah.
Great. Thanks both of you for that one. I think we got time for probably one more question here. This kind of relates to just what you were saying, Ejnar, about the cool climate there versus hot climates. I'll read this. It's a two-part question. So how would you expect the total energy balance to change in hot climates as related to the amount of energy that could be sold back to the utility companies? With Denmark being a colder climate, is there more excess energy available to sell back to the utilities in a hotter climate?
Yes, definitely. There's more energy in the hot climate because, as I said also on the video there, when we were having the tour, in summertime, the refrigeration system is already running as a heat pump, a very effective heat pump though. So that means in summertime, or when we have high ambient temperature, we are producing the most of energy. In wintertime, we manipulate the settings a little bit in the pack controller to let it run in summer mode, even in wintertime. So say it's simple. So yes, we can produce a lot of energy in summertime, but we can also produce a lot of energy in wintertime, as we're saying. But that is not at the optimum refrigeration COP anymore, because then you would have to increase the pressure to create heat. But still, what we are doing with our refrigeration system here, we have produced all the heat, as I said, for the whole year. And the most of the period where we are needing extra heat, we do not even increase the pressure to get more heat out of it. So it's so effective that we are just harvesting the excess heat to heat up our building the most of the period where we have a heat need. So yeah, I don't know if that was answering your question. I hope so.
Maybe I can add small point which is relevant for your store, but also other stores. In winter time, when you need the most heat, your refrigeration system is on the low load conditions, and for that reason, to be able to produce more heat, you need to apply like what we call false evaporator. And on our system, we have it connected. Actually, it is connected to our ground, which is near the store. So we have a ground false load, which provides us quite good stable temperatures through the winter time. So of course, using it to produce more heat when we have a good match with the prices.
Excellent. Thanks, Mark. Thanks, Ejnar.
Yeah, Mark, Ejnar, thank you guys so much. Dean, thank you for being here with me.
Thank you, DJ.
Most importantly, thank you all for joining in on this. Please remember that this has been recorded. You can go back and watch it on demand at any time. And we at Danfoss thank you for the opportunity.
We off?